Hamiltonian graph, traveling salesman problem and NP-completeness. Recap of previous lecture. We have discussed the characterization of line graphs, edge coloring, chromatic index, multiplicity and one factorization. Content of this lecture, we will discuss Hamiltonian graph, traveling salesman problem and NP-completeness. Hamiltonian graph. It was studied first by Kirkman in 1856. Hamiltonian cycles are named after Sir William Hamiltonian, who described the game on the graph of the dodecahedron, in which one player specifies a 5-vertex path and the other player must extend it to a spanning cycle. The game was marketed as the Traveller's Dodecahedron, a wooden version in which the vertices were named for 20 important cities. The definition of Hamiltonian graph. Hamiltonian graph is a graph with a spanning cycle, also called as the Hamiltonian cycle. So, let us see in this particular example, the spanning cycle of this particular graph is shown in the red color. It spans across all the vertices. This particular cycle is called a spanning cycle, which passes through all the, or which covers all the vertices of the graph G, that is the cycle. So, the graph which contains this cycle, spanning cycle, is called Hamiltonian graph. Another example, here we can see this particular cycle, spanning cycle, exists in another graph which spans through or which covers all the vertices of this particular graph. Similarly, all the examples which are shown over here are the example of Hamiltonian graphs, because that contains a spanning cycle within it. Hamiltonian graphs. Hamiltonian path is a path that covers every vertex. Now see, once is may not required. Why? Because path contains the vertices exactly once. So, if a path that covers all the vertices exactly once, then it is called Hamiltonian path. Hamiltonian cycle is a cycle that covers every vertex once. Hamiltonian graph, a graph containing the Hamiltonian cycle, is called a Hamiltonian graph, or we can also say a graph having a spanning cycle is called a Hamiltonian graph. A non-Hamiltonian graph is a graph that is not Hamiltonian. That means that does not contains a spanning cycle, or there is no Hamiltonian cycle present in the graph. They are called non-Hamiltonian graphs. Example of a Hamiltonian graph is shown over here. So, Hamiltonian cycle can be converted to a Hamiltonian path just by removing one edge from it. Here the example, we can see the example of a Hamiltonian path. So, if we start from vertex B, covers through C, then D and ends at vertex C. So, it will start at B and it will finish at E. The path is called Hamiltonian path. Why? Because it covers all the vertices exactly once. Hamiltonian path which we have identified here is B, A, I, H, C, D, G, F, E. So, here this particular path has touched all the vertices. That means it covers all the vertices once. Hence, it is called a Hamiltonian path. Here it is having a Hamiltonian circuit. Let us see this example. We start at A, visit C, then visit B, and then end at to the same point. It is called a circuit, and it visits all the vertices once, that is A, C, B we have identified. This is called Hamiltonian circuit. Similarly, other two graphs we can also identify. Let us start from W, visit Z, visit Y, X and W. It will start and end at the same point, and hence it is having a circuit which visits all the vertices exactly once, called Hamiltonian circuit. Let us take this example also. We start from here and come back at the same point, start and end at the same point and visit all the vertices exactly once, called Hamiltonian circuit. Similarly, these are different graphs shown which are basically the Hamiltonian graphs having the Hamiltonian cycle or a circuit within it. These are the example which are non-Hamiltonian graphs. Why? Because it does not have the Hamiltonian circuit or a Hamiltonian cycle. So it does not have Hamiltonian cycle, therefore they are all non-Hamiltonian graphs. So for example, here in Petersen graph there is no cycle possible. Why? Because these end vertices are having degree 1. This is having Petersen graph is another example which does not have the Hamiltonian cycle, hence this is non-Hamiltonian graph. Similarly, all other graphs which does not have the Hamiltonian cycle within it. So non-Hamiltonian graph example are shown over here, that is the graph with one vertex. Then claw graph is also a graph with 4 vertices. So this is a claw graph. This is also non-Hamiltonian. Similarly, all other graphs, Petersen we have already seen that it is non-Hamiltonian. So until 1970, interest in Hamiltonian cycle centered on their relationship to the 4-color problem. Later study was stimulated by practical applications and by the issue of complexity. So because of the issue of complexity, these Hamiltonian cycles are going to be an important for analysis of the algorithms. No easily testable characterizations is known for Hamiltonian graphs. We will study the necessary conditions. Here loops and multiple edges are irrelevant. A graph is Hamiltonian if and only if the simple graph obtained by keeping one copy of each non-loop edge is Hamiltonian. Therefore, in this lecture we will restrict our discussion to a simple graphs only. This is relevant when discussing the conditions involving the vertex degrees. Necessary condition for a Hamiltonian graph. Here we see that every Hamiltonian graph is 2 connected, because deleting a vertex leaves the subgraph with the spanning path. So we also call it as Hamiltonian path. Now bipartite graph suggests a way to strengthen this particular necessary condition. So a spanning cycle in a bipartite graph visits 2 partites as alternatively. So there can be no such cycle unless the partite sets have an equal size. So take this particular example. This particular partite set has 3 elements, this is 2 elements. So a spanning cycle in a bipartite visits 2 sides. So there can be no such cycle unless bipartite set is of same size. So this becomes a path. To complete a cycle, it has to have another vertex, and then only a cycle is possible. So the partite sets, so a bipartite graph KMN is Hamiltonian only if if m is equal to n. Alternatively, we can argue that the cycle returns to a different vertex of one partite set, as we have seen here. It will return to a different partite sets after each visits to the other partite sets. Proposition. This particular proposition will establish the necessary condition for a graph to be Hamiltonian, or whether the Hamiltonian cycle is present in the graph or not. So, if G has a Hamiltonian cycle, then for every non-empty set S, which is a subset of vertices of the graph G, such that the graph without that set S, that is G minus S graph, has at most the cardinality of S number of components. So, meaning to say that, so if we take a subset S which is not empty, this subset is a subset from the vertex set of that particular graph, such that if we remove this particular set of vertices from the graph, the number of components which will be there should be at most the cardinality of S. So, again let us see, that is stated in the proposition. So, if G is a Hamiltonian cycle, then for every subset S, the graph which is obtained after removing that S, that is G minus S, has at most S number of components. So, that means the graph after removing that S will result into the number of components, and the number of components will be less than or equal to S, that is the cardinality of S. So, let us see the proof. So, the proof says that when, let us take this is G minus S and this is S. So, when this S will be removed, then there will be components, component number 1, component number 2, component number 3, component number 4. 4 components will be there. Now, when leaving a component of G minus S, let us say the component number 1, when we leave, a Hamiltonian cycle can go only to S. So, that means a particular vertex in every component will basically arrive on S with a distinct vertex. Let us say this is V1. Another component, if it leaves this particular component number 2, it will arrive here on another distinct vertex. That means it is not arriving on V1, it will arrive on another distinct vertex V2. Similarly, another vertex, when it will leave the component, it will arrive on another distinct vertex. This particular vertex will arrive on a distinct vertex V4. It may also arrive here. Similarly, this vertex will arrive on a vertex V5, and this particular vertex will arrive V6. So, when a component, when it leaves the component of G minus S, the Hamiltonian cycle can go only to S, and the arrival of S must use the distinct vertices of S. Hence, S must have at least as many vertices as G minus S has the components. So, every component, if it is arriving in on S, after leaving it G minus S, it will arrive on a distinct vertices. So, at least that many number of vertices should be there in S, hence this particular condition. So, the number of vertices, so the number of component of G minus S should be basically at least S. Or we can also say that the number of components of G minus S, if it is greater than S, then there is no Hamiltonian cycle present in the graph according to this particular proposition, which we have already proved. So, here in the definition, C of H denotes the number of components of a graph H. Thus, the necessary condition I have already stated that the number of components in a graph G minus S is basically at most S for all S which is a subset of V. So, that means the number of components should not exceed the number of elements present in S. So, this condition guarantees that G is 2 connected, that is deleting one vertex leaves at most one component, but it does not guarantees a Hamiltonian cycle because this is necessary condition. Let us see the example to illustrate that proposition, which is nothing but a necessary condition for the existence of a Hamiltonian cycle. So, in this particular graph, which is nothing but a bipartite graph, here we can see here that it is not Hamiltonian. That means if we can find out a subset of vertices S in this particular graph, and if we remove, then the resulting number of component will exceed the elements in S. Let us take this vertex V1 and this vertex V2 and remove it from the graph. So, the remaining graph G minus S, S consists of V1 and V2 will have component number 1, component number 2, component number 3, will result in 3 different components. So, the number of components in G minus S, that is V1 and V2, will be 3 here in this case, and the cardinality of V1 and V2 is equal to 2. Hence, the number of components C of G minus V1 V2 exceeds S, which is nothing but a violation of the necessary condition. Therefore, this particular graph is not Hamiltonian. However, another graph which is shown over here on the right side, this graph if we consider, let us remove the 2 vertices. This is one vertex. If we remove, what will happen? If we remove this vertex, and that means still these vertices will be connected, and if we remove this vertex, then there will be some components. The number of components again will be 2, because this will be one component and the remaining will be another component. So, that means if S is equal to 2 and the number of component after removing is also 2, so equal to sign is basically satisfying. So, that means by the symmetry of the graph we can show that for all subsets this particular condition is satisfied. So, it satisfies the condition, but the another question is whether it has the spanning cycle or a, although it satisfies the condition, but we will show that this particular necessary condition is not sufficient for the graph to have the Hamiltonian cycle. Let us start by looking, if we start from this particular vertex and search by walking into the graph edges to find out a spanning cycle. Let us start from this particular point, go to the next vertex, then go to the next vertex and so on, cover this particular vertex through that particular cycle or a walk, and then come back to the same point. So, we start at this point and we finish at this point. You see that we have covered all the vertices. So, this is called a path, because both the endpoints we could not join from where we have started. Hence, this particular path which spans through all the vertices called a Hamiltonian path. But it is not a cycle or a circuit, but no Hamiltonian cycle present. Therefore, so here it has no Hamiltonian or spanning cycle. Therefore, it is not, that is, the necessary condition is not sufficient for the existence of a Hamiltonian cycle that we have shown. So, all the edges incident to the vertices of degree 2 must be used, but in this graph that requires 3 edges incident to the central vertex, and hence the necessary this condition is not sufficient. So, sufficient condition is also required for a graph to be Hamiltonian, that we have already discussed. Now, another important graph which is called a Petersen graph is also a non-Hamiltonian graph which will satisfy these particular conditions. Which conditions? The necessary condition which we have stated. Earlier video lectures we have proved that this particular Hamiltonian graph has 2 disjoint C5 cycles, that is, it is having 2 factors of the Petersen graph. So, it is not a spanning cycle, that means it is not single spanning cycle. Therefore, it is non-Hamiltonian graph, although it satisfies the necessary condition. Here we can see the same necessary condition, that means if we are given 3 components, this is component number 1, this is component number 2, and this is component number 3. Let us find out how many vertices are required for a Hamiltonian cycle to be present. Now, as we have seen in the necessary condition that these are the components, and let us make S. So, let us start from this particular vertex and construct a Hamiltonian cycle. So, we start from this particular vertex, visit this particular node, visit this node, and this particular node. That means there is a spanning path which will cover all its vertices and then leave from that vertex. We are leaving this particular component. So, as I have told that when it will leave, it will basically arrive in S on a distinct vertex. Let us call it as B1. Now, from B1 let us enter again to a different component on a vertex and then visit another node, and let us leave this particular component. It will arrive on another distinct vertex. Let us call it as V2. From B2 we can again enter into another different component, then visit all the vertices on that spanning cycle which we are going to construct, and then leave. So, and then leave this particular component. So, when we leave this component, it will arrive on S on a particular vertex. Let us call it as B3. Now, from B3 we can join from where we have started, and hence we complete the Hamiltonian cycle, which requires that V1, V2 and V3, 3 different vertices are to be present in this particular graph. So, this complete graph which we have shown is a Hamiltonian graph, and we have also constructed a Hamiltonian cycle. Now, to show that it suffices the necessary condition, so Here the size of S is nothing but 1, 2, 3, and the number of components is also 1, 2, 3. So both are equal relation, hence this is, in this particular graph we see that the necessary condition holds. So again we will show the same example, that if we remove these two vertices from this particular bipartite graph, then the number of components is 3, which is exceeding the cardinality of S, that is nothing but 2. Hence this is non-Hamiltonian. Why? Because here it violates the necessary condition for a Hamiltonian cycle to be present. Hence the graph is non-Hamiltonian. Let us take the Petersen graph. Petersen graph also satisfies this particular condition, which is nothing but the lemma for the Hamiltonian cycle, which is the necessary condition is satisfied. That means for any subset of vertices, if we plug out, the number of components will be basically the size of, will be the at most the size of that set S. Hence it satisfies the necessary condition. So we will show here that necessary condition is not sufficient for a Hamiltonian cycle to be present in the graph. Let us see here in this particular example that, let us see that we start at this particular vertex, then we visit the vertices around the cycle C5 which is present. Now we enter into the inner cycle through this particular vertex. Now here we will end. So this particular construction will give you the Hamiltonian path, but we cannot complete the circle or a circuit, hence there is no Hamiltonian cycle, and therefore Petersen graph is non-Hamiltonian. We can also shown that it has the Hamiltonian path. That means we can start from this vertex, we can trace back all the vertices, enter into it, then visit and finish it over here. This is the Hamiltonian path. That we have done. Second part is basically that we have to prove that Petersen has no Hamiltonian cycle. Now we have earlier seen that the Petersen graph in the previous videos, that Petersen graph has two C5, that means two disjoint cycles of C5, that is one cycle is outer cycle, the other cycle is the inner cycle. So this is C5 cycle, two C5 cycles are there in Petersen graph. There are two C5 cycles are there. So the cycle of size 5 of 5 vertices present in the Petersen graph. That means it does not have the cycles less than 5, that is 4 or less than that cycles are not present in the Petersen graph. So this is the observation number 1. Let us use this observation to prove that Petersen graph has no Hamiltonian cycle. Petersen graph has number of vertices as 10 different vertices, and it has number of edges as 15 different edges are there. So 15 edges are there and 10 vertices are there. Let us construct a Hamiltonian cycle. So, we will prove by contradiction. Let us say that C is a Hamiltonian cycle. A Hamiltonian cycle is a cycle which is a spanning cycle of that particular graph. That means it will span through all the 10 vertices. Let us form a 10 cycle, and now we will place an arc. So, this is the 10 cycle. Now, you know that there are 2 C5 cycles are present in this Petersen graph. So, 1 and 5 can have a chord. So, 10 different edges we have used in the cycle. Remaining 5 edges we have to put as a chord. So, this is the first possible chord. Now, there is no 4 cycle or less than 4 cycles, so hence these chords are not possible. So, this is one possible chord. Now, let us take 2, let us take 3, let us take 4. Now, the last one cannot be basically included. Why? Because there cannot be a cycle of length 4 or less than that. Hence, we are not able to construct a Hamiltonian cycle here in this particular graph. Traveling salesman problem. Traveling salesman problem deals with a salesman who plans to visit n-1 other cities and return home. The natural objective is to minimize the total travel time. Now, if we consider a graph that is a complete graph Kn, and we assign each edge with a weight equal to the travel time between the corresponding cities, then we seek the spanning cycle of minimum total weight. This is the famous traveling salesman problem, seemingly analogous to the minimum spanning tree problem, but the traveling salesman problem as yet has no good algorithm. Let us understand traveling salesman problem through a simple example. Here we will consider 5 different nodes. We can draw a complete graph on 5 different nodes. So, let us say that this is K5. Now, here we will find out and we will assign the weights. Let us say Wij is assigned to all these edges the weights. So, the salesman has to start from one point, go to all other cities exactly once and come back to the original city. Here these are the possible traces. For example, start from 1, go to 3, choose by this edge, then go to 4 by this edge, then from 4 it will go to 2 by this edge, and from 2 to 5 by this edge, and from 5 to 1 back from where it is started. This is one such possibility. Another way is that it will start from 1, taking another from 1 it will go to 2, and from 2 it will go to 3, from 3 it will go to 5, from 5 it will go to 4, from 4 it will come back to 1 from where it has started. So, traveling salesman is about finding the least cost path, so that all the cities are visited exactly once and it will return back to the same point. Now, here we will see that there are various possibilities exist, that means more than one ways a traveling salesman can visit the cities and can come back. Of all these different alternatives, possibilities, it has to find out the one with the least cost. So, let us see the how many possibilities it has to explore, that is n minus 1 factorial by 2. Even for the 4 cities it comes out to be 3 factorial by 2, that is 3 possibilities. As we increase the number of nodes in the problem, this particular search space becomes exponential in size and becomes a difficult problem, cannot be easily solved in this manner. Therefore, different heuristics and bounds are given to solve the traveling salesman problem. So, our traveling salesman still awaits the instruction, that is NP-completeness does not eliminate the need for an answer, because it is a practical application and many applications are based on this particular solution of this particular problem. So, we seek a heuristic algorithm that finds the solution close to the optimal. Why? Because finding an optimal may take too much of time. Perhaps we can prove a guarantee about how far from the optimum the result may be. For example, we may be the content to have a solution whose cost is at most twice the optimum if we have an algorithm that can quickly generate a solution. So, such a possibility, that means deviation from the optimum, but with a particular guarantees, are also of practical interest. Therefore, deviation from the optimum with a particular guarantees, those algorithms which compute traveling salesman problem efficiently are called approximation algorithm. So, an approximation algorithm always generates a solution whose ratio to the optimum is bounded by a constant value. If it is not, then those algorithms are not approximation algorithm. Let us take one such heuristics, that is called nearest neighbor heuristic for traveling salesman problem. Nevertheless, the greedy algorithms works well on large graphs generated randomly. Next, we consider a simple heuristic for traveling salesman problem, where the vertices V1 to Vn are the vertices and Wij's denote the weights, your cost of the edges between vertex Vi and Vj. Now, from an arbitrary starting point, it seems reasonable to move to the next vertex via the least cost incidence edge. Therefore, we iteratively move to the closest unvisited neighbor of the current vertex, and this is the greedy algorithm and runs quickly, and this is called the nearest neighbor heuristic. Consider a traveling salesman problem with a weight 0 on the Hamiltonian path, weight n square on all other edges incident to the endpoint of P, and weight 1 on all the remaining edges. This example has many spanning cycles of weight n, but the nearest neighbor heuristic yields a cycle of weight at least n square from any starting point. Thus, the cost of the cycle produced by the algorithm is not bounded by the constant multiple of optimal cost, and it is not an approximation algorithm. So, there is a theorem which says that if there is a constant C which is at least 1 and a polynomial time algorithm A such that A produces for each instance of a traveling salesman problem a spanning cycle with a cost at most c times the optimum value, then P is equal to NP. That means this particular problem also becomes difficult to be computed with the approximation algorithm. Let us take the example of a nearest neighbor algorithm for traveling salesman problem. Now we have to have a starting point. Let us say that the starting point is shown in the green color vertex as B. Now we will choose our second vertex by finding the nearest neighbor. So here the nearest neighbor means the neighbor with a minimum value or minimum cost. Here there are possibilities 1, 2, 3, 4, and among them this is having the minimum cost. So we will place an edge from B to E. Now after reaching E, now we have the possibilities. We can go to A, we can go to C, we can go to D. Now among them this C is basically with the minimum or the least cost. That means from E we can go to A with the minimum cost of 10. Now after reaching A, we can choose between C and D. So we will choose D. Why? Because it is having the minimum cost. After reaching D, we have a possibilities to choose. So C is not visited, so we will choose C, and from C we have to go to B again. So the total cost, if we sum these green color edges, the weights on these green color edges, that total cost comes out to be 49. If we choose another way, that means another starting point, then the cost can also come down to 47. So here in this case, if we choose different starting vertices and use the nearest neighbor heuristics, the total cost we can see that comes out to be 48, 49, 49, 48. So minimum is 48. So by nearest neighbor heuristic, the minimum cost which we have obtained is called an upper bound solution. So that means the optimal solution is upper bounded by this nearest neighbor algorithm that we have obtained in this particular way. So let us review this nearest neighbor algorithm. From a starting vertex, choose an edge with the smallest cost and use that as the first edge in the circuit. Continue in this manner, choosing among the edges that connect from the current vertex to the vertices you have not yet visited. So when you have visited every vertex, return to the original or to the initial or starting vertex. So this particular another example we can see here. In this particular example, we start from C. We have 34, 43, 50. So we will go to A. When we reach A, we have 23, 30 and 29. We will go to B. From B, there is a possibility of 28, 21. So we will choose 21, and then we will reach D. From D we have a possibility to go to E, so we will go to E, and from E we have to come back to C. Now we have to see how to come back to C. There is an edge of 43, so we will come back to C here in this particular case. So all these things, the solution is shown over here, and the total cost comes out to be 165 of this particular circuit which we have identified through traveling salesman problem. Now let us find out the lower bound. Upper bound we have already computed through nearest neighbor algorithm. So to find a lower bound for the weight of the minimum Hamiltonian cycle, we choose an arbitrary node and delete that node and all its arcs. Then find the length of the minimum connector for the remaining arcs and we will use any minimum spanning tree algorithm for it, either Prim's algorithm we will use it. And once the tree is constructed, then we will place the two arcs with the least weights from the deleted nodes to the minimum spanning tree which we have obtained, and that will be the lower bound. Let us take this particular example to understand the lower bound computation for a traveling salesman problem on a given graph with a given weights. Now you see that this particular graph is a complete graph of 5 vertices. So here we are going to delete A and all its arcs will be deleted. So the remaining part of the graph after deleting A will be this much. And now here we have to run the Prim's algorithm. The starting point, we have to choose the starting point, and let us say that we will construct a minimum spanning tree which is shown in the red color, which will span through all the vertices. So if we find out the total cost is 4, 2 and 5. If we add, it comes out to be 11. Now we will place the two edges. So it will be 11. Now as far as A is concerned, we will place two edges with at least two different costs. That means AE was having higher cost, so it is not included. So two edges are added up, 2 and 3. Total cost of the lower bound is 11 of this particular computation, plus two more edges we have added, 2 and 3, that comes out to be 16. So the lower bound we have obtained is 16. So the optimum or optimal solution should be at least 16, and it will be upper bounded by that particular value which we have obtained using nearest neighbor algorithm. Now we can delete some other vertex, let us say a B, and again we run this algorithm, we obtain a different value. Here also we obtain 11, 6, and now we delete C. And now if we see the statistics of computation of a lower bound, how to compute the lower bound is when vertex A is deleted, the value comes out to be 16, when B is deleted comes out to be 17, C is deleted 16, D is deleted 16, when E is deleted it comes out to be. So the greatest value among all is 17, hence the lower bound becomes 17, and then we will apply this one optimal algorithm on these values. Reductions from Hamiltonian cycle to the traveling salesman problem. So reducing from the big problem to a little problem that will solve oblique decide the bigger problem. So let us see this particular notion for reducing the Hamiltonian cycle to a traveling salesman problem. Now Hamiltonian cycle problem setting does not require the graph to be complete. Does the graph contains a cycle that visits each vertex exactly once? That is the only requirement of the problem setting to find out the Hamiltonian cycle. Let us take this particular graph to find out the Hamiltonian cycle in the graph. It need not be a complete graph. We start from a point, visit to another node, visit to next node, and finally come back to the same point. This is the cycle which is a spanning cycle we require, that is called Hamiltonian cycle, which we are searching in this particular problem setting. About the problem setting in a traveling salesman, the graph must be complete. That means the missing edges which is not there in Hamiltonian are to be present to make the graph complete. Second thing is that the graph contains a cycle that visits each vertex exactly once and also should have the cost of total tour is basically less than or equal to k for some given value of k. So, that means it is not any such cycle, but a cycle which is having the total cost less than k. Those kind of cycles are being required here in traveling salesman problem setting. So, with this particular difference, so we are given the Hamiltonian cycle problem, then we can convert it into a problem formulation in the traveling salesman in the following manner. We have to first complete the graph, in the sense the missing edges we have to add so that the graph becomes a complete graph. Now, the question is, if we add the edges, then we require some weights also to be there. So, we have to about this particular weight, and also we have to choose a number, because the total cost of the tour also is to be bounded by some number k, and that number k also is required to be mentioned in the traveling salesman problem solution. Now, the value of k, for example, if this particular graph is given and all the edges are having edge weights as 1, then if we find a cycle in this one traveling salesman problem, then the cycle is of length or a cost 4. So, if we say that find out a cycle of the cost less than 4, that is not possible. So, we have to choose the number k such that we can find out a existing cycle with the minimum cost. Now, if we change the weights of the edges, and we mention that we want a cycle to be of length 4. So, the what should be that minimum value of k to be there in this particular graph, we have to ascertain that value of k. NP-completeness. Intractability, we defined a good algorithm to be the algorithm that runs correctly, obviously, in time bounded by the polynomial function of the input size. Those are called good algorithms. Now, one algorithm for traveling salesman considers all the spanning cycles and select the cheapest one, that is called a brute force method, will not be a good algorithm, because the complete graph of n node kn has n minus 1 factorial by 2 different spanning cycles. So, for a given input size n, the total time which will require is not a polynomial function, but it is an exponential function. Why? Because here n minus 1 factorial by 2, and this has growth faster than every polynomial function n. So, this algorithm is not a good algorithm which we are looking for, hence the computation takes too long for the graphs of any substantial size. Practical applications require solving traveling salesman on a graph with hundreds or thousands of the vertices, where this particular value shoots up, because it is not a polynomial. Hence, it becomes impractical to solve this particular problem using this kind of algorithm. So, are we searching for a good algorithm? So, no one has found a good algorithm for traveling salesman problem, and no one has proved that none of these algorithms exist. The traveling salesman belongs to a large class of problem having the property that a good algorithm for any one of them will yield the good algorithm for every one of other such problems for which the good algorithms are not yet known. So, a good algorithm for B will yield a good algorithm for A if we can reduce the problem A to problem B. As an easy example of this, we can use a good algorithm for a traveling salesman problem B, for example, it is called, to recognize the Hamiltonian graphs, that is problem A. Now, from the graph G, form an instance of traveling salesman problem on a vertex set G by assigning the weights 0 to the vertex pairs that are the edges of G and weight 1 to the pairs that are not present. So, the graph G has a Hamiltonian cycle if and only if the optimum solution to this instance of traveling salesman problem has a cost 0. So, the time for transformation is polynomial in n of G. So, a good algorithm for traveling salesman produces a good algorithm for to test for the spanning cycles. We conclude that traveling salesman is at least as hard as the Hamiltonian cycle problem. So, in the formal discussion we consider only the decision problems where the answer is yes or no. This makes sense for recognizing the Hamiltonian graphs, but traveling salesman is an optimization problem. That means finding a tour with a minimum cost. So, when formulated as a decision problem called minimum spanning tree, the input for the traveling salesman is a weighted graph G and a number k, and the problem is to test whether the graph has a spanning cycle with a weight at most k. Repeated application of this decision problem, at most a polynomial number of applications, can be used to find the minimum weight of a spanning tree. Similarly, the maximum independent set takes a graph and an input k as the input and test alpha G is at least k. So, those problems are called intractable problem. Why? Because the good algorithms are not known, and if one knows a good algorithm of any of these particular problem, then the other problem can be reduced and solved. Hence, we are now going to give the further definition in this class of problems. So, NP hard and NP complete. A problem is NP hard if the polynomial time algorithm for it could be used to construct a polynomial time algorithm for each problem in NP. So, that means those problems are as hard as other problems, and that is why this problem is called NP hard. So, it is NP complete if it belongs to NP, and it is also NP hard if some NP complete problem belongs to P, then P is equal to NP. No polynomial time algorithm is known for any of the many NP complete problems. This is the prevailing belief that P is not equal to NP. So, given one NP complete problem, NP completeness of the other problems followed by the reduction arguments as suggested earlier, we will use it in further discussions. Now, examples NP complete and NP hard problems. We will see the Hamiltonian path problem. The optimization, it is an optimization problem, that is given a graph, find a path that passes through every vertex exactly once. The decision version is that does a graph contains a Hamiltonian path in a yes no problem. This is NP complete. Another example which is called NP hard problem, that is called a traveling salesman problem. Here the optimization version of this problem is to find out the minimum weight traveling salesman problem or minimum weight Hamiltonian path. The decision version of the traveling salesman problem says that given a graph and an integer k, is there a Hamiltonian path with a cost at most k, that is to be NP hard. Now, let us go in more details about the unknown problems, how we are going to prove to be NP complete by the method of reduction, that is called polynomial time reduction. So, we can now populate the set of NP complete problem by transitive reduction. So, reducing one problem in NP complete problem to a new problem means that all the problems in NP complete class transitively reduce to that particular problem. So, the general problem for proving that a new problem L is in NP complete class or not, the general step is to prove that. For that, the two steps are required to show whether L is NP complete problem. So, there are two steps. First step is to show that the problem L is in NP. So, this becomes easy. Why? Because if we can get a certificate, then we can check this certificate in a polynomial time whether it belongs to that particular problem or not, solution of a problem or not, that we can check in. So, the problem we have to show that is NP, we have to check that solution in polynomial time, then the problem is in NP. Second thing is, second step for proving NP completeness is that we have to prove that the problem L is NP hard. For that we have to select a known problem. So, we require a catalog of different NP complete problems. That means we know some known NP complete problem and we select one such problem, let us say L prime. Now, we describe a algorithm A that computes a function f mapping every instance of L prime problem to some approximately constructed instance fx of the unknown problem which we are going to prove to be NP complete. Now, we have to prove that this x, the problem instance in L prime, if and only if the corresponding mapping of that particular problem into an L, into the problem L means the problem which we are going to prove to be NP complete. That means we take a problem in L prime and we map it to another problem that is L, and this particular mapping is to be done by an algorithm which runs in a polynomial time. So, we have to choose, we have to know that what problems are there. So, if we want to prove a particular problem, a new problem to be NP complete, we have to choose one of these particular problem. Let us say circuit satisfiability problem, and we reduce this circuit satisfiability problem to that new problem. This direction is important, otherwise the transitively it will not be able to reduce and hence it will not be the correct solution. So, from a known NP complete problem to a new problem we have to reduce in this particular direction and apply these steps to prove it to be NP hard. Once the problem is in NP and we have proved it to be NP hard, the problem becomes, let us take the example of a clique problem. So, a clique in an undirected graph is a subset of vertices such that each pair of these subset of set of vertices are connected by an edge, that is they are mutually connected set, that is called a clique. So, take for example, this is a graph and K2 is basically a clique present, all vertices if you include that also completes a clique. So, the clique of a maximum size we are searching. So, a clique problem is to find the clique of a maximum size. This becomes an optimization problem. So, this can be converted into a decision version of a problem by asking whether a clique of a size k exists in the graph or not. So, here we are given a pair, that is a graph and a value of k. So, we are asking a question whether the graph contains a clique of size k or not. So, this is a decision version of the problem which will answer in yes or no, and that is called a clique problem. Now, to prove that the clique is NP complete, so first thing is we have to show that the clique is in NP. How we can show this? We can give a certificate and check whether the certificate is basically a clique of that graph or not, and that verification we can do in a polynomial time, hence this can be done. we can do this in a polynomial time, hence the click is in NP. Now, second part is that we have to prove that click is NP hard. To prove it to be NP hard, we have to select one known problem which is there in NP complete. Let us choose a 3 CNF SAT, which is well known NP complete problem. SAT is circuit satisfiability. So, we are given a Boolean function that will basically represent a circuit, and we will reduce this particular problem to the click problem by a clever reduction which is shown here in this particular diagram. Now, the Boolean function is the conjunction of disjunctions. So, the disjunction are nothing but they are the clause. So, let us say that it is 3 CNF, that means every clause has 3 literals, x1 and not of x2 and not of x3. Similarly, here also this clause C2 is also having 3 literals and C3 is also having 3 literals. So, each literal is represented as the node of a graph, and now we will place the edges. We will not place the edges between x1 and x1 not of x1. We will not place the edges between x1 and not of x1. We will place the edges between other parts like x1 and x2, x1 and x3, where there is no conflict, we can place an edge. This graph we obtain. Now, in this graph we will see that the solution to this particular Boolean formula is there if we basically select one variable from each particular clause and assign the truth value 1. So, this particular formula becomes true in that case, and this is nothing but a click. So, if the formula is basically valid, then there exists a click, that means we have converted a click or we have reduced into a click of a graph. So, again let us recall that there is a vertex of every literal, there is an edge between the vertices only if the corresponding literals are different in different triples and literals are consistent, that means x1 and x1 bar are not consistent. So, if there are k clauses, we ask whether the graph has a k click. Such a click exists if and only if there is a satisfying assignment. The fact that there is a k click means that there are k vertices that are all connected to each other. The fact that 2 vertices are connected to each other means that they can receive the same consistent Boolean assignment, and they are in different clauses. Since there are k vertices, then literal form each of k clauses must be satisfied. So, we have shown that click is NP complete in this particular reduction method. Vertex cover, a vertex cover of an undirected graph is a subset of vertices such that if u and v is an edge of a graph, then u is basically taken up in the vertex cover v prime, or v is taken up in the vertex cover, or they are both taken up in the vertex cover. So, the vertices covers its incident edges, and the vertex cover of a graph is the set of vertices that covers all the edges in that particular graph. Vertex cover problem is to find the vertex cover of a minimum size. This is an optimization version of a problem. Now, the decision version of a problem would be that called vertex cover problem is nothing but a graph is given and a k is given, and the question is asked whether the graph has a vertex cover of size k. Now, vertex cover is NP complete. Let us see how we can prove this particular problem to be NP complete. For that, the first step, that vertex cover is NP, is quite easy. So, we give a certificate in the form of a v prime, which is a subset of v, and then we have to check in a polynomial time whether this v prime is the vertex cover of a graph or not, that is it covers, that is all the edges are incident in V prime or not, that we can check in a polynomial time. Now the other part remains that we have to prove that vertex cover is NP hard. To prove that vertex cover is NP hard, we have to give a reduction, that is a polynomial function which will convert a given NP complete problem to the vertex cover problem. So let us choose a particular problem that is called a clique. We have earlier proved that clique is NP complete, so one NP complete problem we will take. Now we will reduce to a vertex cover problem. Now given an instance GVE of a clique, one computes the complement of a graph G. If this G is given, we compute a complement of that particular graph, which we call G complement. So the graph G has a clique of size k if and only if the complement has the vertex cover of size V minus k. So here we can see that in G there is a clique of size 4, all the vertices are connected, we convert into a complement of that particular graph and all these edges are missing. So in the complement graph we will get the vertex cover. So vertex cover will be of this particular size, and this is nothing but V minus, if we take V minus k, these two, the remaining will be that particular vertex cover in the original graph. Now we will see another problem called Hamiltonian cycle. To prove that Hamiltonian cycle is NP complete, we have to show that Hamiltonian cycle to be in NP. That means if we give a certificate in the form of the cycle or a path, we can check whether it is a Hamiltonian cycle or not. That can be done in a polynomial time. Second part, we have to prove that it is NP hard. For that we have to choose one problem which is already there in NP complete problem, and we can reduce that particular problem to the Hamiltonian cycle problem by way of a polynomial time reduction or a mapping. So let us choose the vertex cover, a well known problem as NP complete problem, and we will reduce to the Hamiltonian cycle problem by converting each edge of a vertex cover instance into a subgraph which is called a widget, through which one can find a portion of the Hamiltonian cycle only if one or both of the vertices of the edge are in the covering set. So this is non-trivial problem to convert an instance of a graph into the subgraph of widgets, which is shown over here in this particular figure. Now any Hamiltonian cycle must include all the vertices in the widgets, and there are only 3 ways to pass through each widget. If only vertex u is included in the cover, we will use the path B. That means it will enter from u and it will trace back on the other side of right side of the widgets, then come back, return to the same part right sets and exits from. If only vertex V, then we have to, that means if there is entry at vertex V, then we have basically this particular widget D. Otherwise the path C to include this particular path, that means we enter from U, complete the widget of one side, enter from V, complete the widget from the other side. The widgets are wired in sequences that chain all the widgets of each given vertex. So if the vertex is selected, all of the widgets correspond to its edges are reached. Let us take this example graph, and this example graph is converted into this particular graph of widgets. So, here we can see that if we select a vertex x1, then we can enter through a particular widget w, trace back all the widgets, and then exits out from this particular widget, enters into another set of widgets, and enter into another set of widgets, enter into another set of widgets, go to another vertex of the vertex cover, comes back, then trace back all the other widgets and return back to the same point from where it has started. This is the Hamiltonian cycle. And these two vertices, if there is a Hamiltonian cycle, that means they are visited through these two vertices. So, there is a vertex cover. So, the vertex cover is converted into or reduced into a Hamiltonian cycle problem here with this particular reduction. Another problem is the traveling salesman problem. Traveling salesman problem we have to prove to be NP hard. So, finally, one of the famous problems, suppose you are traveling through different cities exactly once in a Hamiltonian cycle, but this particular tour should be of minimum cost. So, traveling salesman, as I told you earlier, requires a graph to be a complete graph, and every edge will be having a weight to it, and we want to find out a value k, so that the tour should be having the cost with that at most k value. Now, here only exponential solutions have been found to date. That means there is no good algorithms, although it is easy to check the solution in the polynomial time. The reduction represents a Hamiltonian cycle problem, as the traveling salesman problem on a complete graph, but with the cost of edges in a traveling salesman problem being 0 if the edge is in Hamiltonian cycle, and the problem, or if it is 1 if it is not there. So, we can see that we have reduced this particular traveling salesman Hamiltonian cycle problem to a traveling salesman problem, and we have proved that it is basically NP complete problem. Now, as far as traveling salesman problems are concerned, if you know that there are brute force solutions or exist, that means we find out all the different cycles and find out the cycle with the minimum cost, and that will be exponential number of possibilities to explore and then find out the good solution. So, optimal solution. So, this is having an exponential time. Another way of solving traveling salesman is through the dynamic programming, but that also requires the order of n square 2 raised power n, which is also an exponential size search space, or the time is exponential. So, if there is no good solution, so there is a cartoon which says that let us not go on tour and let us sit down. That means it is going to take lot of time to compute the minimum cost. So, we have proved this NP complete problem as the traveling salesman problem. So, in this lecture we have discussed Hamiltonian graphs, traveling salesman, interactability, decision problems, NP hard, NP complete, NP completeness proved by reduction, heuristics and bounds, nearest neighbor algorithm for traveling salesman, and also discuss reductions from Hamiltonian cycle to the traveling salesman problem. Thank you.